Hey everybody, today we're going to be talking about stoichiometry. You'll probably remember having been introduced to this in a previous lecture video, but what we're going to do now is we're going to kind of build on some of the mathematical principles behind a lot of those stoichiometric concepts. So the first thing that we got to recognize is that we're going to be doing mole-to-mole conversions to start things off. The reason that I start here is that eventually we're going to be doing what's called a gram-to-gram mole conversion, but the mole-to-mole conversion is always going to be kind of the central, most important part, and it always depends on a balanced chemical reaction. So let's see a balanced chemical reaction that I just kind of pick at random, and we'll go through a couple of the ways to set up these mole-to-mole conversions. And also we'll talk a little bit about why we have to do this kind of thing. So here's a nice balanced chemical reaction. One of the things that we've talked about already is that these coefficients are really just telling us a ratio. And I think in a previous lecture video, I kind of said it's like knowing how to bake a cake and how many eggs to use and how much flour. That's really all these numbers are telling us. And so keep in mind, at least on the reactant side, it's saying that in terms of a total mole amount, we need 3 times as much hydrogen as we use of the nitrogen, right? So there must be a 1-to-3 relationship. And the next couple of lecture videos are going to be kind of talking about how we use that number and some special situations that can arise when, let's say, maybe you don't have enough nitrogen around, and how can I tell how much product I can form? All of these are stoichiometric concepts that we're going to develop. So the good news is if I kind of do if I think about it as in like a 1-to-3 ratio and just kind of forget about the products for just a second, that's what I need in my reactant, right? Or my reactant side. So what happens if, let's say I have 2 nitrogens now, right? Well, that means that I would then need 6 hydrogens, right? I just pretty much in my head multiplied everything through by 2. Turns out that in that case, I would form 4 ammonias. The problem is that we're not usually talking about just simple single molecule conversions, right? We're talking about big giant numbers of things, and that's where that mole concept comes in. Just like before I said that I needed 1 nitrogen to react with 3 hydrogens, it also turns out that I need, if I have 1 mole of this, right, that huge number, the chemist's dozen, 6.02 times 10 to the 23rd, I need 3 moles of H2 molecules, right? And so that ratio needs to be maintained at all costs in order to truly get the most out of my system. Similarly, if I started with 2 moles here, I would need 6 moles of H2. So those numbers, those are kind of like easier to kind of wrap our brain around. But what it becomes a little bit harder, right? If I imagine, let's say that I have like a situation where I have, let's say, 4.5 moles of H2 gas. Our brains might break down a little bit and say, well, what 4.5 moles, how much nitrogen do I need, right? So let me show you what you do in a case like that. And it turns out it's going to use some of the same dimensional analysis techniques that we've used previously when we were doing metric conversions. So let's go through the following. Let's say that I don't have 3 moles, right? But I have instead, let's pick a really crazy number, like 4.7, let's say. Right? I've got 4.7 moles of H2, and I as a chemist want to know exactly how much nitrogen I need to use, and I don't want to really have to think too hard, right? So question mark, how many moles of N2 do I need? That's where this dimensional analysis technique comes in. And what you're going to do, just like we would do for a normal metric conversion, is we're going to set up a little work area here where we put the number of moles of hydrogen that we have. We're going to put it over 1. And hopefully you guys can see that. It's not too dark. And we're going to convert this into the moles of N2. And you'll remember one of the important steps of a dimensional analysis is always to recognize that I need a conversion factor, and I need those units to go away, which means I need to put them in the denominator, and I want to convert to these units. And so before, in the case of a metric conversion, right, we would have to look this up on a sheet and figure out what number goes where. The one thing that's a little bit of a change is that the numbers that go in there are going to change depending on what your balanced chemical reaction is. So in this case, we know that the 1, right, which is assumed out here, goes with the nitrogen. And the 3 is going to go with the H2. And if you kind of follow through the bouncing ball here and you keep track of your units, you'll recognize that this is really telling us to do is that we need to use our calculators to take 4.7 divided by 3. And that's the number of moles of nitrogen that we would actually need in that case. So let me do that for you, and I'll write down the number. Okay, so I did that division here, and keeping track of sig figs, why not? We might as well. What you can see is I've got 1.56 underlined, which means it's insignificant, right? And so that would be rounded to about 1.6 moles of N2 that's required. Okay? Turns out that this is called the mole bridge. Anytime we use this kind of balanced chemical reaction comparing the moles of one thing to the moles of another, that's going to be the mole bridge. And it's probably the most important part of stoichiometry. And it's always told to you by a balanced chemical reaction. The problem is that, as we're going to see as we kind of develop this video, is it's not always going to be the case that we're given the actual number of moles. Often you're just given the number of grams, and then you have to convert to the moles, do the mole bridge, and then a lot of times you have to convert that number, right, in terms of moles, into grams, right? And so I think about the mole bridge as kind of like the central concept. And those of you that continue in Chem 105, it's a lot of what we're going to talk about in Chem 105 too. It's just that instead of doing the gram to mole and mole to gram stuff to get to the mole bridge, et cetera, is we'll start to talk about different concentrations. We'll talk about different properties of gases that we can also use to get to this mole bridge. But this is really the most important thing, is setting up this dimensional analysis. So I'm going to do one more example. And probably let's just use the same exact reaction, and we'll see how we can use a conversion factor, another conversion factor that's given to us, to determine how many moles of NH3 could actually be formed. Okay, so let's start the process in the same way, right? We know that we've got 4.7 moles of H2. Let's try to determine how much product we can actually form, right? And so now we need to know the number of moles of NH3 that can be formed. Turns out it's no different than what we did before. It's just now we have kind of a different ending value. So we're still going to say, well, that means I've got 4.7 moles of H2 all over 1. I have a conversion factor. I know what I want to convert to, which is this moles of NH3. And I'm just going to keep track of the units and put the numbers where the units tell me to put them. There's my moles of H2. My moles of NH3 go up here. And I'm pretty sure that you all can read that, assuming I don't put too much shade on it here. So what numbers go here? Well, it turns out we're simply going to find H2 in the balanced chemical reaction. And then we're going to find NH3 in the balanced chemical reaction. And now what this is telling us to do is we're essentially multiplying by 2/3, right? We're going to do that times 2 divided by 3 in order to get to our answer. So there, the 9.4 divided by 3 that I know that I need to do. So I'll plug that into my calculator. And now there's my final answer, right? 3.1 essentially, to keeping track of sig figs. Moles of NH3 can be made from 4.7 moles of H2. Again, it doesn't matter how complicated this balanced chemical reaction is. It could be the most complicated one in the universe. As long as you know the coefficients that go in front, you can convert the moles of anything into the moles of absolutely anything else. What you'll see in the next couple of segments of this video is instead of starting with moles, I'm going to start out with some number of grams of something. And then in the end, I'm going to convert to how many grams of something else. And you'll notice that it really is just a combination of the last set of video lectures on gram to mole conversions, but now incorporating the mole bridge. Now we'll go through some gram to gram conversions. These are the much more common type that you'll see. Chances are, if I ask you about this on an exam or something, I'll kind of help you stepwise through it, right? We'll do like a gram to a mole conversion, then a mole bridge, mole to mole, and then we'll do a mole to gram conversion at the end. And I'll kind of stepwise guide you through it. Of course, in your homework, you need to be able to do all these steps independently. So it's still valuable to kind of go through the full game here. So first of all, let's say that I start with, what's an interesting thing to start with? Let's say that I know that I formed a certain number of grams of ammonia, and I want to figure out how many grams of, let's say, hydrogen that I might have used, right? And I could, of course, go the other way. It really doesn't matter. All we're going to be using is these ideas of ratios. So let's say that I have 10 grams of NH3, and I want to know how many grams of H2 that would have been required, right? The one thing that you don't want to do is you don't want to go directly into the mole bridge, right? You have to make sure that we do some conversions first. If you do that kind of, that use the ratio of this like 2 to 3, and you think, well, that must mean that I need, 15 grams of hydrogen gas because you happen to be really good at math and can do those in your head. Well, it turns out that that would be incredibly wrong because different compounds or different elements have different amounts of junk in the trunk, right? There's a different number of grams per mole in both of these things. So it's not quite that simple. We can't launch right into that ratio analysis yet. So I always think about it, the second that I see grams anywhere in this class in concept of mole and stoichiometry, first thing you always have to do is convert things into mole. What do you need for that? Well, it turns out that we need some information about the molecular weights of these things, or molecular masses, I think I called them in a different video. So first thing I'm going to do is calculate the molar masses and put them above the two items of interest here, and then we'll carry through the calculation. Okay, so I erased the top just to give us a little bit of room to do some of these calculations, and let's actually do them in the black marker because I think those show up the best. So very first thing that we always got to do, second you're given any information about grams, is convert that into moles. So let's set up a dimensional analysis. We've got 10 grams, and in this case I always put of what, right? Just to kind of, if nothing else, let me give you partial credit when you guys do this kind of thing on your exams. If you show me what you know, right, it's probably going to be better than just assuming that I know what you're thinking. We're going to put a conversion factor, and the very first step is to convert this thing into moles. I do the same steps that I've learned again and again having to do with dimensional analysis. I say, what units do I have here that I'd like to cross out? That's the grams of NH3. I want to convert that to the moles of NH3. And this is where I have to be careful that I use the right numbers. What number goes with grams? What number goes with moles? And that's where I remember how to do my gram to mole conversions, and remember that this information tells me that there are 17.03 grams in exactly 1 mole of ammonia. So we can take advantage of that. Turns out that the 17.03 goes here. The 1 goes up top. And then we carry through, and that tells us to figure out the true number of grams. It's going to be 10 divided by 17.03 because these units will cancel. Once we get to that point, we'll know the number of moles of just NH3. I'm going to list that off down here just to kind of so that we can kind of keep track of all the information that we're calculating. And then we'll go to the next step, which is the mole bridge. So there are the number of moles of NH3. By the way, in terms of my sig figs, I assumed that this guy was a 10 so that we actually have 2 sig figs in our calculation here. And honestly, I don't care too much about sig figs. I'd rather have you guys understand what's going on in these numbers. So now that we've got moles, that's that intermediate point where once you've gotten moles of one thing, now we want to convert to the moles of some other thing. So in order to set up this very next part, I have to remember where I want to go. One of the things that starts to get confusing with stoichiometry is you kind of forget where the heck you're going once you start. That's why I really like to have like a nice balanced chemical reaction with all the data just written right in front of me. So hopefully, if I remember to put a question mark here, it kind of guides me to what I'm supposed to do. I've got moles of NH3. Ultimately, I want to end up with grams of H2, but I can't do that directly, right? I have to do the mole bridge first. And so that's what I've listed off up here, right? We've got our conversion all written out and ready to put in all of the conversion factors. I know that I've got the moles of NH3 down here, the moles of H2 up here. Anytime I see moles over moles, right, that's a clue that I have to look at a balanced chemical reaction. What numbers go where? Well, I can see that the 3 goes with H2, and I can see the 2 goes with ammonia. So when I multiply those together, the moles of NH3 cancel out, and so essentially I've got that times 3 divided by 2. So there's that division. There's my result. I'm trying to keep everything nice and lined up so I can keep track of all these bits of data, right? I'm looking at that, I'm sniffing it, I'm saying, does that sniff right? Yeah, that sniffs kind of right? It should be in a 2-to-3 ratio, so the math, kind of seems to make sense. Now the very last step is for me to take this moles and to finally convert it into the grams. And if you remember, a mole to gram conversion, that just requires the molar mass, which I've written already of H2. I'll show it up top, and then we'll get our final answer. We've got our number of moles of H2. We want to convert to grams. Let's keep track of the units. We've got moles of H2 on the bottom, grams of H2 on the top. We look at this and remember that it's 2.02 grams and exactly 1 mole. So 1 goes with the mole, 2.02 goes with grams. And then we've got our answer finally. This times that divided by 1, which is just that. And then that tells us how many grams of H2 we have. So it looks like we're ready to report out our final answer. So sig fig wise, we're going to say that is exactly 1.8 grams of H2. One of the things that's true of all of these that I've done 3 different dimensional analyses for, you can put it in a big giant dimensional analysis as long as you're good at the technique. The problem with that is kind of twofold. One is generally on an exam, I'll ask you about kind of the stepwise way of doing things. And if you kind of blow by it, you have to then do work to kind of get back. So I wouldn't suggest doing it for that reason. Also, if you're not feeling too good about dimensional analysis, to have 3 conversion factors is a little bit dangerous. So I really do encourage you, if nothing else, just so that I can give you some partial credit, showing each one of these steps individually. And honestly, you can stop at any point, right? Like if I just wanted to know the number of moles of H2, I wouldn't obviously have to have done that very last mole to gram conversion, right? And so keeping an idea of where you're going into dimensional analysis is also sometimes really hard. I could show you a whole bunch of other examples of this, which I'd be more than willing to show you in office hours. The problem is that until you actually just start doing some homework, you won't really know where you're going to get lost. So I'd say right now, stop this video, go on and do a couple of homework questions. Inevitably, it'll be kind of tough, but then it's going to be a great thing for us to talk about in office hours. Thanks for bearing with me for this long one.